Okay, so in this problem we have a box is sliding with constant speed, so there's no acceleration, and it's going at 4 meters per second in the positive x direction, so it's going from left to right on a horizontal frictionless surface. At x equals 0, the box encounters a rough patch of the surface, and then the surface becomes even rougher. So the surface is initially frictionless, and then between x0 and 2 meters, it has a kinetic, the coefficient of kinetic friction is 0.2. And then between 2 and 4 meters, the coefficient of friction is kinetic, is 0.4. So we want to know when does this, so this box is moving, right? We want to know when does it, where does it stop from x equals 0? How far does it stop, and what time? How long does it how long does it take to stop? Okay, so if you've seen me do these problems before, you know that there's a quote unquote traditional way of solving it, and you can see on my screen, and you can possibly pause the video, and you can see this. This is great if you like to do this. I like to do it in a more approachable, I think a more common sense approach, and so that's what I'm going to show you here. A different way using graphs, some common sense, and then of course some algebra, some calculus to solve it like from scratch without having to use any of these equations. All right, so this problem, I'm calling it a rough patch. And you can see here we have a box on the left, and we don't know its mass. So its mass is m. So in the problem, it actually did not state the mass, so we don't know what it is. V0, the initial velocity, as it said, is 4 meters per second, and it's not accelerating, so the acceleration currently is 0 meters per second. It is accelerating to the right, so you can see the arrow is going from the left to the right, so it's accelerating to the right. And you can see, let me just do this so you can see what I'm talking about. Like right here, this from 0 to 2 meters, you can see that the coefficient of friction is 0.2. And then here from 2 to 4, it's 0.4. Okay? And then after 4 meters, which is right here, after 4 meters, there's no more friction. So the question it asks is essentially where does it stop? Because this box M is moving, right, from left to right. Where does it stop? Now the question is, does it stop anywhere from 0 to 4? Like, does it stop anywhere in this area right here? Or does it stop beyond the area? Let's say it stops right here. Well, it wouldn't stop right there. Because if for some reason the box kept going, like it had a velocity greater than 0, let's say in this area right here, it would never stop. It would go on forever because there's no friction here. So if it did actually make it past 4 meters, it would go on forever because there's nothing stopping it. So because they want you to know where does it stop, obviously it has to stop somewhere between 0 and 4. It has to be somewhere in that area. Like the answer is not infinity. So it has to stop between 0 and 4. The question is we have to figure out where is it going to stop between 0 and 4. Okay, so that's the setup. I'm going to just kind of erase some of this stuff just so I can refer back to it and it's not messy. Okay, great. So this is the setup. So remember, the box is going from left to right, 4 meters per second, and I want to know where is it stopping at between 0 and 4, between 0 and 4 meters. Okay. So what we're going to do is I want to create a free body diagram, okay, of the box. So I'm going to do a little dot right here. This dot represents the box, and I'm going to just write in all of the forces on it. So if we look back here, obviously the box, when it hits the red area, the red patch, it's going to slow down because there's some friction there, right? So, but how much is it going to slow down? Like, what's the acceleration? What's the acceleration once it hits that red patch? And we need to figure that. Once we figure out what the acceleration is, then we can kind of figure out how, when is it going to stop? Okay, so we got this dot here. The dot, like I said, represents the box, and I want to put on all the forces. So there is a weight right? It's pulling it down. That's gravity. That's the force of gravity is pulling it down. And then because of Newton's third law, there's also another force called the normal force, which is like the floor is pushing up on the box. So that's the normal force, and that's going up. And then there's a force this way. And this is F. I'm gonna call it F. You can say F for force, or you can call it friction. So I'm gonna also do a subscript of K, meaning kinetic friction. It's not static, because it's not stopped. It's actually moving. So this is the kinetic friction. Okay. So I have three forces: the normal, the force, the weight force, and then friction. Now, normal and the weight, these two are equal. You're like, how do you know they're equal? Well, because if they weren't equal, then it would be accelerating in the up, down, or in the y direction. Because it's not, they have to be equal, right? The normal force has to equal the weight. Like I said, if they weren't, it would be moving in the up, down direction, or y, and it's not. Okay. Okay, cool. So we know then that you could also say the sum of the forces in y equal 0, right? If I sum them up, so if the normal force is positive and the weight force is negative, if you add those two together, you should get 0, right? And so that means that the normal force then equals the weight force, right? Or N minus W equals 0, or N equals W. Okay? So that's cool. What about, and that's in the y direction, but what about the x direction? What about the x direction? So there is some net force. So this is Newton's second law, right? So this is between here and here. So the weight is pulling down. Therefore the table or the surface is pushing up. So this is Newton's third law, and then here where the sum of the forces are 0, that's Newton's first law, and then now we're going to do Newton's second law, which is the sum of the forces are not 0, right? So if it's not 0, that means that there is some acceleration, and that's going to happen, right? This thing is going to accelerate. Well, it's going to accelerate. It's going to slow down. Okay, you could call that a negative acceleration. Okay, so the sum of the forces. So this is y. Let's do x. So the sum of the forces in x equals mass times acceleration, right? So this is Newton's first law, and then this is his second law. This is his second law because it's not 0. This is the first one means it's like a constant velocity, or zero velocity, and the second one is no. There is a net force on it. So if there's a net force, that means that there's also an acceleration. Okay. So sum of the forces in x equals mass times acceleration. Great. So what is the force? Well, you can see here that it's Fk. Okay, Fk. That's my friction force. Okay, and call it my friction force is equal to mass times acceleration. Okay. So what else do we know? Well, we do know that weight is actually mass times gravity, right? M is whatever my mass is, I don't know what it is, times gravity. So what's the normal force then? Well, the normal force, because it's exactly the same as W, is also mass times gravity. It's also mass times gravity. And then this Fk, or this frictional force, is your coefficient times the normal force. Okay, times the normal force. So if I know that, then what I can do here is I can take this thing right here, which is Newton's second law, the force, the friction, the kinetic friction, the force due to kinetic friction is equal to the mass of the object times its acceleration. Remember, I'm trying to look for the acceleration. So Fk, I can replace Fk with mu n. okay? And then that equals mass times acceleration. Remember, because Fk, so Fk is equal to that. And then ma, of course, is still ma. And then n right here is just mg, right? From here, right? Remember that? So mu is still mu, and then n becomes mg. mg equals ma. And then I'm just going to divide by m. Get rid of that. I don't know what's happened. Sorry. Divide by that. And now we have mu g is equal to a. So the acceleration is equal to mu g. So that means your coefficient of friction times gravity is your acceleration. Okay, in this scenario here. So great. So that's pretty cool. So that's all we have to do. Now, if you want to on this graph, you could show like acceleration is going in this direction. Acceleration is going that. Remember, acceleration is a vector, just like force is a vector. So if the force is going in this direction, right, then the acceleration also has to go in that direction. Has to go in that direction too, okay? Meaning it's negative. So the acceleration is negative. Because the force is negative, therefore the acceleration is also negative, okay? So it's a negative acceleration. Okay, cool. Now that we know that, what I'd like to do is, so now we know the acceleration. Well, there's really two accelerations, right? There's this acceleration in the red area, and then there's the acceleration right here in the blue area, right? And they're going to be different because it's mu g. So this one is mu 0.2 times g. This is 0.4 times g. Okay, let me just erase that. Okay, so we have two accelerations. All right, so now what I want to do is I want to draw an overall sketch of what's going to happen. So I'm going to do velocity in x, because we're only going back and forth, or x, and this is time. And the initial velocity, as it tells us, is 4 meters per second. So this is 4 meters per second. And what's going to happen is it's going to deaccelerate from 0 to 2 meters. You know, something like that. For 2 meters. Right? And then it's going to deaccelerate even more from 2 to 4. Maybe something like this. And so that this would be another 2 meters, right? So there's 2 meters here and 2 meters here. Something like this. Now, the first slope, this one right here, remember, acceleration is when you're doing velocity versus time, the slope is the acceleration. So my slope here is just, remember, it's mu g. So mu g here is negative 1.96, negative 1.96. That's the slope, or you could say t if you wanted to. And then here it's negative 3.92, negative 3.92. So this is 0.2 times 9.8. Your coefficient times gravity, and this is 0.4 times 9.8, okay? And now the reason it's negative, because so you can see here, that's a negative slope, and that's acceleration, t. Why is acceleration negative? Because up here you can see here the acceleration is negative. It's pointing left. And our positive direction is pointing to the right. So that's why it's negative, okay? Now, the problem with this is we have two separate functions. We have this function here that's going from here to here. And then we have another function that goes from here to here. And so what I want to do is I want to break this problem up into two pieces. I want to break it up into piece 1 and then piece 2. Okay, let me actually go back. Piece 1 and then piece 2. And then we'll just analyze them separately because they are separate functions. And then that'll just make it hopefully a little bit easier. Okay, great. So let's do the first one. So remember, I'm just going to take this thing right here, and I'm just going to make it a function, and I'm going to make this thing here a function. All right, so let's go back. All right. So for number 1, actually this is too big. Let me do this right here. I'm going to do the velocity in x versus time, and I'm going to do its position in x versus time. Okay, so the initial velocity is 4 meters per second, and we know that it is we know that the function looks like this. Looks like this. Now, where does it hit the 0 line? We don't know. Where y equals 0? I don't know. But for right now, let's just kind of just draw that, and we'll say this slope is negative 1.96 t. That's the slope because that came from up here. Remember, it's mu times g plus 4. Plus 4, because that's my y-intercept, right? That's my y-intercept. Great, so I got that. So what I'd like to do is I'd like to find out where does that meet. Remember, because this slope goes until it hits what? 2 meters, right? At 2 meters, which is right here, it transitions into another function. So I want to know, when does this function, the negative 1.96 t, when does it actually hit 2 meters? When does it achieve 2 meters? Okay? Sorry. All right. Okay, so what we'll do then is we'll take this guy and we will integrate it. So we're going to take this function and we're going to integrate it. And if you integrate it, you're going to end up with something like this. So my initial position is 0 meters. Remember, you're like, how do you know that? Because it shows up here. Right here. This is your origin. Let me change it to this color, or this color right here. This is my origin right here. My origin is 0. Okay. So I'm initially at 0, which is right here. And the graph is going to look something like this, roughly speaking. And if you take negative 1.96 t plus 4 and you integrate it, you get negative 1.96, and you take half of that and you do t and you square it. So it's 0.98 t, you square it, and then you take the 4 and you make it 4t plus 4t. Perfect. Now, what I want to know is where does this function hit 2? Because I want to know when does it achieve 2 meters. And so we'll just put like 2 here somewhere. 2. We don't know really where it is, but we'll just put 2 here. And so 2. There's this line here, the 2 line, which looks like this. And then there's the other line, this one, or 2 functions. The red function is negative 0.98 t squared plus 4t. And then the other one, make this, and this is green. This is the green function. So y equals negative 0.98 t squared plus 4t. And then the other function is y equals 2. So I have 2 functions. And what I want to know is where do they intercept each other? Of course, you can look at this and go, well, they probably intercept like right here. Let me just change this color to this. Or this. Right here. Well, they also, they either, so this is what's going to happen. Either it doesn't. Either you get imaginary numbers once you solve for t. Either you get all imaginary numbers, or you get one real number and one imaginary number if it just hits it once. Or you get 2 real numbers. That case, it hits it twice, okay? So either you're going to get 2 imaginary, 2 real, or 1 real, 1 imaginary. So what we're looking for is at least 1 real, okay? At least 1 real. Now, if we don't get a real, that means it doesn't even achieve 2 meters, okay? But if we do get 2 values, two real values, you want to take the first one. You want to know where does it hit 2 meters first. And of course, if you solve for t using like the quadratic formula, solving for t, you actually will get 2 values because it actually does hit that. You could graph it out too and look at it if you want to. But it turns out it actually achieves 2 meters. At 0.58 seconds. 0.58 seconds, it achieves it. Okay. And so you over here somewhere you could say 0.58 seconds. Okay. It will achieve 2 meters. All right. And so, okay, so that's cool. So, yeah, so you can see here, let me just color this in. So this area from here to here is 2 meters. That is 2 meters. Because if you do negative 1.96t plus 4, that function, if you do it from time equals 0 to 0.58 seconds, you'll get 2 meters. Okay? Great. So now what I want to do is I want to know, after 2 meters, remember this box is moving from left to right. I want to know what velocity is it at after it's hit 2 meters, right? So the velocity here, if we go back, the velocity is initially at, let me make this red. The velocity is initially 4 meters per second. But where is it here? What's the velocity here? I don't know. And so what I can do is, if I can figure out what this velocity is here in this box, then I can analyze this final function. Okay? So 0.58, let me just change this back to black. So 0.58, basically you do this. So you're looking for this is the velocity as a function of time is equal to negative 1.96t plus 4. And you just pass in 0.58, right? You take this 0.58, you pass it in as the time, and then what pops out? Well, what pops out is the velocity. And so if you do that, then you will get 2.86. So it turns out, at this time here, let me erase this. Yeah, perfect. It's 2.86 meters per second. So the box is initially going. It's at point 0. It's 4 meters per second, and then after it's traversed 2 meters, it's now slowed down to now 2.86 meters per second. Great. So now that we know this, now that we can make an additional graph. So we've already analyzed this function. We just analyzed it completely. Now it's time to analyze this function. Okay. Let's do it now. So this is my velocity in x, and this is time. Now this function is, we already had it right here. All right, you had it right here. Negative 3.92. That it's your mu times g. Negative 3.92. Okay. So it's somewhere here, and it's negative 3.92 t. It's negative because remember the acceleration is going in the left, where it's going from right to left. Now where is this point right here? Where is this point? Well, it's 2.86. So where we ended off here, where it ended, is where this one starts. 2.86. So we just made a new function. As long as you know the starting point of where the function starts, like, okay, I know where it starts, I know where this is, and then you know how it continues, the negative 3.92, then you're cool. Okay, so this function is negative 3.92t plus 2.86. That completely describes this function. Okay, now we know this function eventually hits hits this, because if it hits this point right here, what does this mean? What does this point right here? This point means no velocity. So it means that there's no more velocity. It stopped. It has to stop, because remember, if it doesn't stop, you end up somewhere over here, and that means it'll go on forever. So it has to stop somewhere. It has to, somewhere in this function, it has to stop, meaning it has to reach 0. It has to reach a 0 velocity. Okay, sorry. So that's what this is. This point represents a 0 velocity. Great. But what's this? But how many meters is this? How many meters is it? I don't know. So What I can do, though, is I can say I have two functions now, right? I have this function here, y equals negative 3.92t plus 2.86, and I have this other function, which is right here, 0. And what I want to know is where do these two functions intersect? Where do they meet at? So what I can do is I can just create an equation, negative 3.92t plus 2.86, which that was your initial conditions. Where does this function, make that one, that's the yellow one. Where does that function equal the blue function, 0? Where do those two meet? And if you solve it, you'll get t equals 0.73 seconds. Okay, and so that's right here, 0.73 seconds. So starting from here, at 2 meters, 0.73 seconds later, it will stop. I don't know where it is, like somewhere over here, it'll stop, okay? But where is that? That's what we're going to find out now. Okay, so now I have a right triangle. You see that? I have a right triangle. And I'm trying to find the area. Sorry. I'm trying to find this area right here. The area, remember, is... the area is the distance covered, right? The area is the distance covered, okay? So I need to find that. But guess what I have? I have this. I have the height of the triangle, and I have the width right here. I have the width of the triangle. So what I can do is I can say, if I want to find this area here, remember area equals 1/2 times your base times your height. The area, I don't know what that is equal to 1/2 times your base, which is your time, 0.73 seconds, times your height, which is 2.86 meters per second. And so if you do all that math, you'll end up with 1.04 meters. 1.04 meters. Okay? So if we go back to this original one, 1.04, that's 1.04. So this ends up being 2. This ends up being 2 meters. This ends up being 1.04. 1.04 meters. And the time from here to here was 0.58 seconds. And the time from here to here was 0.73 seconds. And so if you add those up, you'll get, and I'll put those at the top, you'll get 1.31 seconds. And then if you add 2 meters, which is here, let's go back. Look at this one. You get 2 meters. It went 2 meters. The block went 2 meters, and then before it stopped, it went an additional 1.04 meters in the red. And so 2 plus 1.04, of course, is 3.04. 3.04 meters total. And so that should be the final answer, which is right here. So when the block initially hit the patch, the rough patch, it went 1.31 seconds, and in that 1.31 seconds, it ended up traversing 3.04 meters. So that's what we're looking for: 1.31, 3.04, and if you look back up here at this one, 3.04, and then 1.31. So you can see we got the same answer. Now, if you compare, what I did here, it definitely looks longer, but that's because I just made a lot of graphs, right? It's right. This consumed a lot of visual space because there's a lot of graphs going on, and I don't know. I actually appreciate this better because for me it's more intuitive to see like, oh, okay, here it is. Here's the box. It's slowing down. Okay, and then it's slowing down even more. And I'm using, the free body diagram to try to figure out what the acceleration is. And then I'm trying to figure out, oh, okay, now that I know what acceleration is, I'm going to make a graph number 1, solve it, and then I'll from the solutions of that, I'll create another graph or another function. And then I'll just combine the results together to create my final results. once again, some of you may look at this and go, I enjoy the traditional way better, but for me, I like this. This is more intuitive, and it helps me, gives me a better understanding of what is actually happening than just a wall of equations. So anyway, that's it. Hope you enjoyed it.